So I am recording now. And let me ask, before we launch into a review for exam 2, does anybody have general questions about anything? Again, you can unmute or just type in the chat, whatever you want to do. Okay, not seeing any questions. So let me just mention again, there are directions for this exam. And again, I'll go over them again on Wednesday for the benefit of those who aren't here today. And they're right there at the beginning when you open it up. And you'll have an hour and 40 minutes, just as if we were in class. And please understand, I'm going over a lot of review problems. So my idea is to do half of them today and half of them on Wednesday. I would anticipate that would take, almost the full time that we have set aside. But there aren't that many problems on the exam, okay? I can easily imagine somebody looking at what we're doing in the review and assuming, oh my gosh, there's no way I can do all of that in an hour and 40 minutes. Agreed, you can't. So anticipate about half the number of problems, but I want to make sure you're aware of the types of things you should be able to do at this point in the course, okay? And if you ever have any questions about that, like, what about this type of problem, or what about that type of problem, or how do I know to do this, please ask. The whole point of having live online classes is that we're all together at the same time in the same place. So you're able to ask questions as we go along, okay? I know it's tempting, having taken my share of online classes myself, it's tempting to just kind of lurk in the background and just watch it like it's a video. But face it, you can do that later if that's really what you want to do. Okay, the benefit of being here now is to ask questions. Okay, so let me get started. And the first thing I'm going to do is share my browser. And I just want to do that to show you what I'm using. Okay, here we are in week 8, which, by the way, folks, by the end of this week, you are halfway through the course. Okay, week 8 is the midpoint. Okay, and I am going to be using practiceforexam2.pdf. Okay, so I've kind of taken that file and spread out the questions a little bit. Okay, this file actually has just the answers in it. Okay, but what I've done is spread out the questions a little, and I'm going to actually show you how I worked them out. Okay, and when we're done, of course, the video and anything I use as a file will go into these live online sessions. All right. Okay. So without further ado, let me get started by sharing. Again, I need to bring up my tablet and share that with you. So give me a sec. Alrighty. And let me try this. So I'm here. And let me share it. Okay, so now what you should see, okay, is a file called Practice Test 2. And again, these are the questions that are in that file that I showed you in our course. So again, what I'll do is work through them. Okay, I might occasionally ask you for input. Like I said, it's real tempting to make this just like a video with no interaction, but that's not very fun for you, and it's certainly not fun for me. So let's get some conversations going, okay? Alrighty, so let's get some conversations going. All right, so again, if at any point you have questions, feel free to either type them in the chat, okay, or shout them out. Just unmute yourself temporarily and ask a question, not a problem, okay? I'd also encourage you, if you're going to put stuff in the chat, share it with everyone rather than with me privately. Otherwise, that creates some kind of weird discussions people aren't sure what I'm replying to. Okay, so again, let's get going. All right, so the first one is real simple. It's find the derivative, and I've got a polynomial here. So you can see what I need to do is to just use the power rule for finding the derivative. Okay, and so if I wanted to find y prime, that would be 3 times 5 is 15, drop the exponent by 1, and then on the 2x, okay, that's 2x to the first. So to take the derivative of that, I'd have 1 times -2 is -2, then have x to the 0, which is 1. Okay, so that becomes a constant. The constant plus 1 doesn't give us anything. Okay, so there's my derivative. All right. I'll try to pause a little bit at the end of each question to see if anybody has concerns or wants to ask anything. But again, please, don't expect me to keep typing in the chat any questions, just shout them out or type them. Okay, so there's our plain vanilla derivative, right? And as we move down in the problems, you'll see each one of them gets a little bit more complicated as far as what you have to use in order to take the derivative. Okay, if you look at number 2, okay, f of x is a function composition, right? It's a cubic inside of another cubic, okay? So since it's a composition, I need to use the chain rule. Okay, so in order to make that happen, how do you do that? Well, in words, the chain rule makes a lot more sense than if you write it out in math, okay? The chain rule says, differentiate the shape of the outer function, which looks like something cubed, okay? The way you differentiate something cubed is you bring down the 3, you write the something, and you drop the exponent by 1. Okay, so there's the derivative of your outer function, okay? And then you take the derivative of your inner function, which is the stuff inside the parentheses. Okay, and that's, again, if you look at that, that's the thing that was question 1. So we kind of already know how to take the derivative of that. That's going to be 15x squared minus 2. Okay, and again, anything that's after this is algebraic simplification. All right, so what you want to notice is the structure of this. There's the derivative of the outer function. Here's the derivative of the inner function. Okay, if you were doing this on paper, I'd say stop right there. You don't have to go any further. Okay, not clear how much simplifying more wants you to do. So again, what I'm asking folks to do for this exam is the same thing I asked you to do for the last exam. And that is, when you're ready to start the exam, have all of your materials there, including some paper, and work out each problem on paper before you type it into more. That way, what you can do after the fact is you can either scan in your work or take photos of it and email me the work. That way, if you got this far and for some reason more wanted you to simplify it, and so it didn't give you credit, I will give you credit, okay? Because you did the calculus part correctly, all right? Everybody understand that, okay, about the work? Okay, so I will stop and ask you this. Everyone understand how to show? Okay, everyone understand how to show work on the exam? Okay, with the last exam, exam 1, only about 2/3 of you actually gave me anything. So, if you don't show me work, I can't give you any partial credit. The point of showing work is, to kind of get around the fact we're dealing with a rigid computer system that's grading the problems. Okay. All right. Okay, great. Let's keep going. With problem number 3, Okay, what I would suggest you do here is rewrite it. Okay, rewrite the radicals. Oops. The radicals so they have exponents. Okay, and again, the point is, you should have enough background in algebra to be able to do that. Okay, it makes the calculus a whole lot easier. So I'm not doing any calculus yet. I'm just rewriting these like this. Okay, now take a look at that second fraction. Okay, the cube root of x to the fourth is in the denominator. That's telling me that x would have a negative exponent on it. Okay, so I'm going to write x, negative sign. Okay, negative exponents make fractions. They don't make things negative. Okay, so the fact that that x term is in the denominator is why I'm using a negative exponent. The next thing you want to remember is roots are in the denominator of your fraction and powers are in the numerator. So the way I would write this is x to the negative 4 thirds. Okay, the 3 is the cube root. Okay, and the 4, of course, is the power on x. Okay, you got to be able to get to that step or you can't get off the starting line. Okay, now again, it's just using the power rule because everything has power on it. Okay, and here's the calculus step. Bring down the 1/2 as the coefficient, okay, and drop the exponent by 1. Well, I'm at positive 1/2, so subtracting 1 makes this negative 1/2. Okay, and again, feel free to use whatever tools you want to use, okay, in order to play with the exponents. If you've got a calculator that does fractions, use it. Okay, with the next one, I'm going to bring down my the exponent as a coefficient, which is negative. Okay, so rather than saying plus a negative number, I'm going to get rid of my plus sign and write negative 4 thirds. Okay, then I'm going to subtract another 1 from a negative exponent, which is going to make it more negative. Okay, so negative 4 thirds minus a whole 1, which is another 3 thirds, makes this negative 7 thirds. Okay, and that's the calculus step. Okay, I'd almost be willing to bet that Moore wants you to simplify this only in the sense of write it with radicals again, but let's just do that. Okay, in my first term, okay, you can see 2 is in the denominator, but the negative exponent on x means it's also in the denominator. So this becomes 1 over 2 to the square root of x. Okay, because 1/2 means square root. In the second term, the 4 is in the numerator, the 3 is in the denominator, and the negative exponent on x means it's also in the denominator with the 3. So I'll write it like 4 over 3. Okay, and then let's take a look at this. This is the cube root of x to the 7th. So I can write it like this. All right, and that's as simplified as you can make it. Everybody okay with that one? Okay. So again, most of the work in this problem wasn't calculus. Most of the work was remembering properties of exponents. All righty. If we look at number 4, you can see, oh, it's got a radical. I should probably rewrite that with exponents. And you'd be correct. So let's rewrite the radical. Okay, and you'll see me say that over and over again. Okay, so not doing any calculus, just writing this quantity in parentheses with 1/3 as the exponent, because that's how you write cube root with a radical, with an exponent. Okay. Now you can see I've got some quantity raised to the 1/3 power. Okay. So now you can see easily that it's a composition. Okay, it's a quadratic inside a cube root. So I need to use the chain rule. Okay. Again, a large part of doing calculus like this is understanding what you're looking at. Okay. So again, the way you do that is you first bring down your exponent and just rewrite the thing in parentheses, and then subtract 1 from the exponent. So 1/3 minus 3/3 is -2/3. And then take the derivative of what's inside here, the inner. Okay, so I have the outer, then times the inner, and that's 2x. Again, there can be a whole lot more simplifying here, but again, I want to kind of just show you the calculus bit. Okay, in order to be able to get full credit on an exam, you got to get to this point. Okay, so that said, why do we bother to simplify algebraically? That seems like something people invented just to drive students nuts. And that's not true. Okay, if you're doing any kind of modeling with calculus, the whole point of algebraic simplification is actually meant to be a help. Okay, because chances are you're going to do something else with what you just took the derivative of or did calculus on. Okay, and if you simplify it, it's going to be a lot easier to use that for something going forward. You can think of it like this. Calculus makes things bigger and bigger and bigger and messier, and then algebra brings them all back together and makes them nice and small so you can work on them again. Okay, so that's the point of the algebraic simplification. Again, if I wanted to simplify this, okay, this 2x would be in the numerator of my answer. Okay, the 3 and this would be in the denominator of my answer. So let me just quickly show you what that would look like. Okay, and then I have 3 times, well, what does this say? The negative sign puts it downstairs, and then it's the cube root of this thing squared. Okay, or you can even just write it like this. Okay, that's simpler. Okay, if you want to write it with a radical, you would say the cube root of this quantity squared. Okay. Again, I don't want you to be scared off by the algebra. Again, it's supposed to be your friend. But that said, it's a calculus class. And as long as you can get here, I'm happy. Okay. All righty. Let's look at number 5. Okay. Number 5, okay, if you look at it, is a linear bit and something in a square root. Okay, so again, if I'm going to rewrite the square root, with exponents, okay, and this should just be a habit when you're doing calculus. Okay, I'm going to stop and actually ask you guys a question. Okay, what do I have in number 5? And I'm asking you, how should I proceed? What do I have? And you recognize it. Anybody? How would you go forward with this? Yeah, pretty much. You've got a product. Okay, you've got a product of what? A linear And what's the other thing? The other thing's a composition. Okay, good for you. Everybody is good again. Okay, this part over here is a composition of a quadratic inside a square root. Okay, so product of linear and composition. So first you're going to need the product rule. And then when you're differentiating the pieces, you're going to need the chain rule. Okay. Now, again, please don't get stuck on what I call the pieces. Okay. I know in your text, they call them F and G. I grew up in math calling this U and calling this V. Okay. So again, we could call them Harry and David. It wouldn't matter. Okay. The point is that they're two separate functions. Okay. So let me differentiate them. Okay, the derivative of 2x is just 2. And the derivative of v is a little more complicated because it's a composition. That would be 1/2 x squared plus 1 to the negative 1/2. And then the derivative of the inside 2x. Okay, so there's the chain rule. Okay, and I'm going to do a little bit of simplifying before I actually put it into the product rule. Okay, because again, I don't want it to get too unwieldy. If you notice the 1/2 and the 2x, the 2's will cancel because this 2's on the bottom and this one's on the top. So you'll wind up with x on top. This quantity will be down in the denominator with a square root on it. Okay, so I could simplify this as okay, everybody all right with that? Again, I'm just using algebra to make it a little bit easier to carry around. Okay. And then here's my product rule. Okay, and again, please don't get stuck on the fact that, wait, in the book it says do, F prime first, and then it doesn't matter when you're doing this. So I learned it like this, u times u prime plus u times u prime. Thing to remember, it's one function times the derivative of the other plus the second function times the derivative of the first. Doesn't matter what order you do them in, okay? Multiplication is order independent, and so is addition. Okay. So then I just go back and I pull my pieces in. Okay, so my u prime is, what I did u first, so 2x times v prime, which is this thing I just came up with. Okay, and then I want u prime times v, and v was my original x squared, square root of x squared. Okay. Again, if you can certainly simplify this a little bit more algebraically, okay? But for now, I'm going to leave it like this, okay? Pretty much what I would do if I wanted to simplify this. Let me just explain a little bit. You can see, first of all, I'd have a 2x squared up here, okay? If I multiply these two x's together. And then if you think about this as 2 times the square root of x squared plus 1, if you wanted to actually combine these two terms, you would need to multiply this second term by the square root of x squared plus 1 on the top and the bottom. Okay, that's multiplying it by a fancy form of 1. Okay, that way you'd have a common denominator and you'd be able to add the two fractions. Okay, so again, I'm not always going to necessarily show you how to algebraically simplify. Okay, I might show you on the notes I upload, okay, but rather than take a whole lot of time to do it here, again, I'm just kind of explaining what I would do next. Okay, so here would be my next step. Okay, over All right, and you might remember this from intermediate algebra. You can multiply by a fancy form of 1, right? And that will give me a common denominator here. It will also get rid of the square root in the numerator, okay? Because the square root of something times itself is squaring it, okay? So this will give me 2 parentheses, x squared plus 1, which then, guess what? You can combine with this term up here, okay? So you're going to eventually wind up with 4x squared plus 2 in the numerator, okay? So again, just looking down the road algebraically, if you do want to start simplifying things, okay? All right. Any questions at this point? I find that a lot of students, what they have trouble with in a calculus class is not calculus. It's remembering all this algebraic trivia, okay, and using it to get the junk out of the way, okay, so they can actually do something useful with what they performed calculus in, okay? So again, don't hesitate to ask algebra questions. Okay, let's take a look at number 6. Number 6 is a quotient, okay? And again, I've got 2 terms in my denominator, so I can't do any funny business like I would be able to do if this fraction were upside down. I'd be able to just divide through a power of x, okay? I can't do that here. So I am stuck using the quotient rule. Okay? Which if I want to state here, it's f prime of x. Let's say f of x looked like this. Okay, and again, numerator I call u, denominator I call v. Okay, you can call them whatever you want. And f prime of x equals u times u prime minus u times v prime over v squared. Okay, so the trick in remembering this is remembering start with the function in the denominator, multiplied by the derivative of the other one. Okay, and the order in this rule matters because you've got a subtraction and a divide, and those are order dependent. Okay, so this one has to be correct. Remember, when you take the exam, you're allowed to have all of your materials there. I did put a sheet in the first week when we started talking about derivative rules that shows you all these rules with examples, okay? If you took your own notes while you were doing homework, that's even better, okay, when you were doing the reading. Okay, so there's my quotient rule. And then all I need to do is to identify u is x, v is 1 minus x squared. Those look relatively simple. So if I do u prime, that's a 1, right? Because that's x to the first, bring down the 1, drop the exponent by 1 is x to the 0. So that becomes a constant. V prime, okay, the 1 doesn't give me anything, but negative x squared gives me negative 2x. All right, and then it's pretty much plug and play. Just put the expressions in there. Okay, so starting out with v times v prime minus u times v prime, whole thing over v squared. Okay, and again, I'll point out to you here, okay, of course, this first part would just be 1 minus x squared. The second part would be minus 2x squared. Okay, so your numerator would become 1 minus x squared minus 2 squared. Okay, which you can see, this is a minus. I lost a negative sign. You guys, you didn't tell me. Okay, so again, My derivative v prime was negative 2x. So now I have minus x times negative 2x is plus 2x squared. Okay, over 1 minus x squared. Okay, and negative 1 plus 2 is a positive 1, so this simplifies to 1 plus x squared over 1 minus x. Okay, so that's a little bit of algebra there. Okay, again, if you can get to this point and not lose the negative sign like I did, okay, you're good. Okay, so again, make sure you can get at least here in your work. Okay. All right, let's look at some more interesting problems to take the derivative of. Okay, here's an example in number 7 where I do have a single term in the denominator. Okay, you may certainly use the quotient rule on this. I prefer not to use the quotient rule on it. What I'm going to do is a little bit of algebra, and I'm going to divide each term by the denominator. I can get away with that because the denominator is just a single term. Okay? Problem is, most folks are used to going from here to here. You're used to adding and subtracting the stuff in the numerator and putting it over a common denominator. The process works in both directions. So you can split a sum and difference that's in the numerator that's over a single term. You can split it like this. Okay, what does that buy me? Well, I can use my rules of exponents to simplify things. Okay, here I have 4 divided by 2, that's a 2. X to the 4th divided by x squared, remember to subtract the exponents. Over here, you can see the x squareds will cancel, and I'll just be left with a constant, minus 5/2. That's going to be easy to differentiate, right? And then with this last one, the only simplifying I can do is to divide the 8 by the 2, and that will give me a plus 4 over x squared. Okay? Again, with this last term, I would rewrite this as plus 4x to the minus 2. Why would I do that? Because it's a lot easier to differentiate if I've written it with a negative exponent. Okay, and now I have something I can just use the power rule on. Okay, so this is a prime example of algebra being your friend. Okay, if you can see that you can algebraically simplify it before you get started, differentiating it's a whole lot easier. Okay, I'm looking at this over here. Okay, so I'm differentiating my first term. Okay, that's going to give me 4x. Differentiating a constant, negative 5/2, doesn't give me anything. And then differentiating the plus 4 times x to the minus 2 gives me minus 8x to the minus 3. Okay, just using the power rule. And if you want to rewrite this last term, okay, with positive exponents, the 8 would be on top, because again, the 8 isn't being raised to any power, so that stays up in the numerator, and that winds up in the denominator. Okay, and again, if you had decided to use the quotient rule on this, you would have probably gotten the right answer. It might look a little different, okay, but basically, however you decide to differentiate it, as long as it's legitimate mathematically, you're fine. It's kind of like there are multiple ways of solving a quadratic. Some people go straight for the quadratic formula. That will work, but it's kind of messy. All right, same thing here with the quotient rule. That'll work, but it's kind of messy. right? All right. My next problem, question 8. Question 8 is an exponential. Okay, so what's the base? Okay, so I'm asking you a question. What's the base of the exponential in number 8? Anybody? Yeah, it's 4. Okay, and that actually matters, okay, because if you remember the pattern for taking the derivative of an exponential, it's going to look like this: ln of the base times the original exponential times what? Okay, turns out you've got a chain rule going on here, okay, because you've got a linear in your exponent, okay, so you need the chain rule. Okay, it's not just x up there, okay, otherwise we'd be done, okay, so times the derivative of the exponent. All right, here's the chain rule bit. Okay, you'll notice I spend some time like figuring out what I'm going to do before I do it. Okay, so that's helpful. Like, what am I looking at here? Okay, so here goes g prime of x equals ln4. That's my base. My original exponential was 4 to the 0.01x. And then the chain rule bit, the derivative of the exponent, well, that's just 0.01. Okay? And there isn't a whole lot you can do here. Okay, you can leave it like that. It's more conventional to put the number, the actual number first, and then say ln4. Okay, both of these are numbers. Okay, so they're like coefficients. Then put the exponential bit first. But that's just convention, right? All of this stuff's multiplied together, so it doesn't matter really what order you put it in, okay? This is perfectly correct, and if you leave it that way, I'll be fine with it, okay? This is just more conventional notation. All right, everybody all right with the exponential derivative? All right, now let's take a look over here at number 9. Number 9 is also an exponential. Again, exponentials have your x up in your exponent. But this one is a base e exponential. So again, if you wanted to differentiate it, okay, I had to have ln base e times original. And again, this has a whole quadratic function up there in my exponent. So quadratic, move the chain rule. All right, so the last step is simply take the derivative of the exponent. Okay, so you can see how the chain rule makes a very simple change to your derivative of an exponential. You're just multiplying ln of the base times your original function times the derivative of the exponent. Okay, now ln base e, this is 1. Okay, that's asking you ln base e is saying, what do I have to raise e to get e? And the answer is 1. Okay, so I'm not going to write anything for that, but I want to show you it follows the same pattern. All right, so this would be my original function, which is e to the 5 minus x squared, okay? And then the derivative of the exponent. which is negative 2. Okay, so because ln base e is 1, it doesn't show up as anything in the final answer. And again, it's more conventional to say negative 2x e to the 5 minus x squared. Okay, so you put your numbers in any powers of x ahead of the exponentials. Okay, but I'm all right. All right, so questions on exponential derivatives. Anybody questions on how we did those? No, we're good. All right. Well, number 10 is a log derivative. Okay, and if you remember, it's log base e, right? That's what ln means. Okay, so the basic pattern for a log derivative, okay? And again, notice you have a function inside the argument to log. That means you need to use the chain rule. That's because you've got a quadratic inside a log, okay? So the basic shape of it is going to be like this, if you remember how it goes. Okay, you have 1 over the argument, okay? And you would typically have your ln base e down here, okay? But then ln base e is 1, so I don't need that. And then you have the derivative of the argument, okay? And that'll be in the numerator, okay? This is the chain rule piece over here, right? So starting out, I have f prime of t. I notice my variable t. Okay, so start with 1 over 3t squared minus 4t plus 12. And then differentiate this. This is going to be differentiating the quadratic argument. Okay, and you can just put one on top of the other. Okay, and it may be possible to reduce this further. Okay, if you divide out some common factors, factor the quadratic, you just got to get here. Okay, everybody all right with the log one? Everybody okay with the log derivative? All righty. All right, number 11, if you look at it, is a product. Okay, it's a product of an exponential and a cubic. Okay, so what I'm going to need an exponential derivative, a power, derivative, power rule derivative. Okay, and I'm going to also need to use the chain rule because my exponent on e has that 2 in it. So I'm going to need product rule, power rule, and chain rule. Okay, it's really, really important to figure this out before you start. Okay, because it's real easy to get lost in the weeds once you begin. Okay, so again, I have f prime of x. Well, let's start out with the statement that says if f of x equals a product u times v, then f prime of x would equal u times v prime plus u times u. Okay, there's my product rule. Okay, so now all I need is my u's and my v's. U equals e to the 2x b equals x cubed. You split apart the product and then differentiate. Okay, you might remember here, I have a base e, so ln base e is 1. So just repeat this, and then take the derivative of the exponent, which looks a lot better if I write it like this. Okay, e prime equals 3 squared. And then everything else is just putting things in, okay? So first I have my u times v prime plus v times u prime, right? And that's good enough, okay? But you can probably tell there's common factors in here, namely this, okay? And if I were to factor out e to the 2x, what would I be left with? I'd be left with 3x squared from the first term and 2x cubed from the second term. Okay, that looks a whole lot neater. It's also easier if you think about it. If you had to, say, set this to 0 and maybe solve for values of x, it's much easier in this form than it is here, okay? Because you've already factored it. So here's your final result. Okay, any questions on that? Okay. Now the remainder of the problems, there's 24 problems in this review. We are gonna almost be halfway through them. My idea is to go as far as we can go by 10 o'clock, because from my past experience, okay, exam review kind of overwhelms people. They wind up with their eyes rolling back in their head, okay? So I don't want to like bombard you, but I do want to get past the middle because the problems in the second half require a little bit more thought. Okay, these are pretty much like lifting weights, okay? You can kind of do it without thinking as long as you have the patterns, okay? The rest of the problems are more like, okay, what are you going to do with this calculus that you just created, okay? So let's see how far we can get by 10, right? And at that point, we'll decide what to do afterwards. Okay, so here's problem 12. Okay, and problem 12, you can see, is not a simple just find the derivative. It's asking you to find the equation of a tangent line to this curve at this point of tangency. So the important thing is to remember this point is on the tangent line. Okay, that's the point of tangency. It's where the tangent line touches the curve. Okay, so somebody want to explain, how do I start? How do I start? What do you need in order to write the equation of a line? Okay. All right, I've got one suggestion. Tuyen saying, I need the slope. Okay, what else do you need? Okay, Tuyen saying, take the derivative to find the slope. Yes. Okay, so we're going to get the slope from the derivative of the function. Okay, and then you need a point. Okay, so you either need 2 points, and then you're finding the slope. Okay, but they didn't give us 2 points. They gave us an equation and a point of tangency. So what we're going to do is take the derivative to get the slope, and then use the point of tangency to build the rest of the equation. Okay, so first let's take the derivative to find the slope. Okay, and again, I'm trying to be a little descriptive of tangent at 0, -1. Okay, so basically we're going to find the derivative. That'll give us an equation. Then we're going to plug in the 0 value for x. Okay, so let's start out with this. Okay, I pretty much need the quotient rule in order to take the derivative. All right, so that's going to be, if you remember, v times u prime minus u times v prime over v squared, where u is my top function, my numerator function, and v is my denominator function. Okay? Then differentiating these are pretty easy to differentiate. Okay, u prime gives me 2x, and v prime, lo and behold, also gives me 2x. All right, so then I'm going to plug these into my formula, which is v times u prime minus u times v prime, the whole thing over v squared. Okay? Now, it would probably be definitely worth it to me because I'm not done with the problem. Okay? I probably want to simplify this a little so I can go forward, because the next thing I need to do is I need to figure out what the value of this is. Okay? At x equals 0. Okay, now you could plug in a 0 here, and here, and here, and here, and here, and figure out what you've got. That's certainly reasonable. But this isn't that hard to simplify. I'm just going to distribute, factor out my 2x this way. Okay, so rather than distributing the 2x, I'm going to factor it out. And you can see I've got x squared plus 1 from the first term. Okay, and then a minus x squared minus 1 in the second term. Okay, it's important to remember that, again, the minus sign distributes to both of these. Okay, so I'm just factoring out the 2x. Okay, and going a little bit further, this gives me 2x, x squared plus 1 minus x squared plus 1. And you can see the x's cancel, and I'm left with a plus 2 on the top. So this is going to give me 4x over. Okay, and that's a whole lot easier to evaluate. Okay, so here's the calculus bit. These two steps are algebraic. Okay, and now I just plug in x equals 0 to get the slope. Okay, so m is going to be 4 times 0. That's easy. I just have to make sure my denominator is not undefined. 0 squared plus 1 squared. Okay, that's going to be 0 over 1. So my slope is 0. Okay, does everybody understand why I'm evaluating it at x equals 1? I mean, x equals 0, rather. Okay, because this is the point of tangency. You want to know what the slope of the tangent line is right there. Okay, so you need a number, not a function. Okay. Next, find b. Okay, there are multiple ways to do this. Some people use point slope form. I like to start with y equals mx plus b. Okay, and I know my slope is 0. Okay, and then you just plug in 0.01, 0, -1. Okay, so -1 equals 0 times 0 plus b. -1 equals b. Okay, so now what do I have? I have, here's my b value and my slope value. So let's build the equation. Y equals mx plus b. I get y equals 0x minus 1. Okay, so basically what I got was a horizontal line. Okay, so the horizontal line y equals -1 is tangent to this curve at this point. Okay, let us kind of start number 13. Number 13 is more of a physics problem. And I realize that not a lot of folks who take MAT213 have taken physics. That's okay. We can kind of walk through it, right? And again, there's just a few things to remember, okay? First thing is, if you've got a position function like this, okay, velocity is the first derivative, acceleration is the second derivative, okay? So again, velocity, which they're going to rename v of t, equals s prime of t. It's the rate of change of position with respect to time. Makes sense, right? How fast you're moving is how fast your position's changing. So this is just a straight power rule derivative. Okay. So that's really all I need for that. Okay, the acceleration function a of t is just the second derivative. It's the rate of change of your velocity. Are you speeding up or are you slowing down? Okay, so I'm just going to differentiate my first derivative. Okay, so 3t squared differentiates as 6t. 12 doesn't give me anything. Okay, so see, again, this is more of a terminology thing. Okay. Everybody all right with that? Okay. Now, here is the weirdness, okay, about the way they do things in physics. Okay. When the particle is moving forward, its position function, s of t, is increasing. Okay, so its position s of t is increasing when it's moving forward. Okay, when it's moving backward, its position function is decreasing. Okay, now you know how to do that with your first derivative. Okay, basically finding the increasing, decreasing intervals. Okay, so all you need to figure out is when s prime of t is positive. Okay, so first derivative is positive. Okay, so a positive first derivative means the function's increasing. Okay, well, I got an expression for that. Okay, and again, I can add 12s to both sides. Okay, then I can divide both sides by 3. Okay, and you might remember, if you've done anything with quadratic inequalities, this is saying t squared is greater than 4. That happens when t is greater than 2 or t is less than -2. Okay, now we said, okay, t is time, right? Time as a negative number doesn't make sense. Okay, so we would say the function is increasing, okay, moving forward when t is greater than 2. Okay, so again, I threw out the negative value of time because negative time doesn't make sense. All right, since this might be new to those of you who haven't completed all of the homework, okay, I want to make sure everybody's comfortable with this. Okay, with part C of number 13. Okay, with 13, part C. Okay, you can also graph your position function, right? And you can check to see when it's increasing. Okay, with Desmos, it's a lot easier to find the turnaround point. Okay, the problem happens when the turnaround point's not an integer. Okay, so in this case, it's easy. Okay, so when is the particle moving backwards? That's when my s prime of t is less than 0. So 3t squared minus 12 less than 0. Same algebra steps. Okay, and again, this happens when t is less than 2, okay? And also when t is greater than -2. But we're not starting time at -2, okay? Time starts at 0. Okay, so I really can't start at -2. I have to start at 0. So I'll say 0 less than t, which is less than. Okay, so in the interval between when I start timing this particle and 2 seconds, okay, then the particle is moving backwards. Okay, so it starts out by moving backwards, then at time t equals 2, it starts moving forward. Okay, is that part okay? All right. Now find the distance that the particle travels, okay? Split it into the forward and backward motion. Motion by time, okay? So backward, up to t equals 2, and then forward, they're asking you up until t equals 3. Okay, so the easiest way to do this is to just build yourself a table and evaluate s of t. So here's what I might consider doing. All right, now I'll say, okay, so I have a bunch of time periods. I have 0, 1, 2, 3. And if I evaluate the position, I'm going to plug in 0 into my position function, 1 into my position function. That's s of t, right? Here are the values that come out of that. Okay, now here's what you want to think of when you think of position. Imagine a starting line, okay, where the thing is started, okay? So what's happening here, okay? There's a 0 starting line. At time equals 0, the particle is 3 meters in front of the starting line. Okay, so it's not at the starting line, it's 3 meters in front of it. That's what this means. In the first second, it manages to move from 3 meters in front to 8 meters behind the starting line. That's a change of what? What's the change in position? What's the change in position? From 3 ahead of the starting line, yeah, to 8 behind it. Okay, and you might remember, how do you do this? You could say -8 minus 3, or 3 minus a -8, but it's a change of 11 meters. Okay, so it's moved 11 meters. Okay, remember, in this time period, up till 2 seconds, it's still moving backward. Okay, so from -8 to -13, it's gone backwards another how many meters? From -8 to -13. Yeah, okay, so 5 more meters, right? So you can say -8 minus -13, right? So here's 5 meters. Okay, now this is the point at which it turns around and starts moving forward. Okay, so you can see it goes from 13 meters behind the starting line to 6 meters behind the starting line. Okay, that means it moved forward how many meters? Yeah, 7 meters. All right, and then just add these up. 11 plus 5 is 16, plus 3. It moved a total of 23. Okay, so that's the easiest way to explain these physics problems without getting into a whole lot of physics theory. Okay, any questions on the physics problem? Everybody good with that one? Okay, well, this is the point at which I am going to go stop sharing and go back to the meeting. Okay, because I honestly think an hour and 10 minutes is more than enough of review at once. Okay, so any questions on anything we covered? Any questions on what we reviewed? Okay. When we meet next time, we are going to be talking about how to use the first and second derivative to do curve sketching, to determine where things are increasing and decreasing, as well as to determine concavity.